Okay, people seem sort of sat down in a... Hi, I'm Jonathan. Happy to be here. Very happy to be here. I actually used to live sort of this part of the world-ish. I did about 2 years in Slovakia. I live in Sweden at the moment. Beer is horrendously expensive. Yeah, well, the wages are sort of okay as well, so it all works out, I guess. So I work on Perl 6 stuff a bunch of the time. When I'm not working on Perl 6 stuff, I'm working on other stuff, which my day job at the moment normally means teaching topics in software architecture and those sorts of things. It's kind of good fun. When I want to escape my computer, I go and visit places like this and enjoy being outside. And I'm still wondering, like, what does it take to work from outside? Nice. Spend far too much time indoors in this job. So, what I want to talk about today is a bit of stuff that I've been working on for, well, a while. I guess we're talking about Perl 6, so a while is always, you know. So yeah, well. So I contribute to a project called Rakudo. I'm one of the lead developers on that. I didn't ever mean to be. I sort of said, oh, I'll do this one feature, and then got sucked in, so loads of other stuff. So what's Rakudo? It's a Perl 6 implementation. That means a couple of things. It means that it's part compiler, and it means that it's part sort of library of all the built-in things. We've had about 64 monthly releases to date, so we should cut a release every single month. It's very good development discipline. I try and do that on a lot of projects now, just because it sort of really makes you try and keep your mainline branch in an always shippable state, which is a good thing. And I'd say we have sort of 10 to 15 people who are listed, who committed in this release list. But in reality, there's lots of people doing stuff that we depend on as well. Sort of ecosystem things, test things, and so on. So, what about compilers? What does a compiler actually do? Because I think that we can kind of see them as this black box where we throw program source in and some magic happens and then we get something out that's kind of compiled and then it runs and it all works. So what's in there? Compilers love trees. Compilers are all about trees. Text is basically a horrible thing to work with. The sooner we can get rid of text, the better. So basically the first thing a compiler does is look at your text, the source code, and say, how do I turn this into something that looks like a tree so that we can actually do something interesting with it. So basically we do go through a process of what we call parsing, which is taking the various pieces of your code and building a tree, and then we sort of fiddle around and we make other trees, and we take trees and walk over them and make them into better trees, and eventually it pops out something that we can call a target tree, which is a tree that represents the program in a very sort of close way to the target system or runtime that we want to run the program on. And then finally we flatten it out into a bunch of bytecode or assembly or something like that. So basically compilers are things that have sort of textual or flat things at the boundaries, and then they sort of build these tree structures and other data structures up as they go and do the work. So you can generally divide compilers architecturally into two big sets of things. There's a front end, which is all really about the language. So the front end is focused on what does the language's syntax look like. Now that we know about the syntax, what does each bit of syntax mean? So, what does while mean? What does if mean? What does class mean? What does sub mean? Okay, we have to give all these things meanings. So it worries about those, and it has to worry about declarations. So if I declare the variable A, then I have to know from that point in the program for the rest of this lexical scope that when I say $A, then that's referring to that particular bit of storage. And it goes a bit further. When I write the class, I name the class, and then I should be able to refer to it, and it refers to a thingy which contains whatever I put inside of that class. So that's the front end. It's all very language specific. The backend, by contrast, is all about the runtime that we're sort of targeting. So the backend is very much about things like code generation, mapping these sort of higher level concepts like ifs and whiles and other sorts of loops into the things that low level things to think about, which is basically go-tos. That's what we have really in assembly. So it's sort of flattening it all out into something that's sort of a bit closer to what you run. So that's what the backend is. And typically, we sort of see compilers as a bunch of stages, and that's the way we factored it inside of Rakudo. If you go and look at what we do, we basically take the source text and we take it through the parsing and what we call action space, at which point we get a tree which represents the program and its meaning, and then we have a bunch of objects which talk about its declarations. And then we take that tree and we feed it into the optimizer, which spits out an improved version of that tree. And then we take that and we give it to some kind of backend, which then turns it into a sort of more low-level tree and so forth. So basically what we're doing is we are sort of building our compiler out of these very isolated stages. And each stage takes some previous stage's output as its input. It then does its work and it returns the output. So essentially it's a very sort of functional programming-ish design. Each stage is just really a thing that sits there on its own, and we give it something, it does its job, it returns it, and it's all over. So one of the most important trees inside of the Rakudo Perl compiler and in the toolchain in general is something we know as cast. The AST bit stands for abstract syntax tree. What does abstract in this case mean? It means it's abstracted away from the syntax of the language. So how do you spell, sub in some language? Well, it might be called fun if you're NML. We might not even have a keyword for it if we're in Java or C#. So lots of languages have different ways of expressing things. So they have different sort of syntactic conventions for doing things. Well, we sort of only care about those for the initial parsing phase. We don't really care about what the program originally wrote that much beyond that. We care about what the program means. And that's what an AST is all about. It's about capturing the meaning. So here we can see that we've figured out that we've got some variable here, which we're going to call x. We have an integer value, which is a 1. And we're going to take the 2 and do some kind of addition, integer addition in this case. That's what the underscore I is. So basically that's what these trees look like. And of course they're pretty big. Once you get a fairly interesting program, they're enormous. But really, cast is at heart a relatively simple AST format. We only have 15 different types of nodes. Not that many. That's one of the interesting lessons we've learned, actually. Having fairly few of them goes an awfully long way. And it actually helps in many ways to sort of keep it relatively small as well. So when I first joined the project, I was looking at the set of AST types. I was like, no way. We're going to need like at least double or 3 times this amount. We'll need nodes for classes, nodes for all of these things. And well, I was wrong. No, we did not need that many, and we never have. So it's kind of been one of those lessons. So I have a computer science background, which means, of course, I went off to the Komsky compiler construction course and sat in the class and listened to the very energetic lecturer actually talking about compilers. Well, he was pretty entertaining to watch, and he taught you all the normal stuff. The trouble is that when it comes to building PLPW, the stuff you learn in compiler class at school is kind of necessary, but it's not quite sufficient. So trying to just take those ideas and say, okay, I know how to build a PLPW compiler. Yeah, no you don't. So what makes PLPW kind of interesting? Why do we have some of the challenges? Well, one thing that is slightly unusual, but not really that bad, is that we have to keep the compiler available and callable at runtime. So, here we have an eval, and eval shows up in various places. So here is when I want to go and do, hey, it's green. When I want to go and do a pattern match here, and I want to interpolate this regex actually as a pattern, then what I need to do is put it between these angles. If you just write $pat, we match it literally, which means that you have to try really hard to get regex injection these days, which is kind of nice. So, that really is a form of eval as well. And eval is a little bit interesting in that the most useful thing about it is that you can actually see symbols in the containing lexical scope. Okay, so when I actually, write say here, the reason that I can call say is because I can see the say that is in the sort of lexical scope of where I did the eval. And you might say, what? Lexical scope say? And say is just a perfectly normal function, just a normal subroutine in Perl 6. And the built-ins form the outer lexical scope of your program. So basically everything is very lexicalized. Now that one is not too much of an engineering challenge. I mean, it is, but it isn't. It's not a huge deal. The one that's a real bit of fun is that you can actually do bits of runtime at compile time. Okay, so here we're at check time, and we say, and we take the current time now, and we subtract the now that we got at begin time. So these actually, begin runs at the point you hit it, and check runs at the end of the compilation time. So this is actually doing the incredibly useful job of telling you how much time elapsed between when you hit this line when you were passing the program and the time at the end of passing the complete program, which is probably useless, but it sort of gives you an example. Now, the other thing is that, what about this constant declaration here? What if I want to make the factorial constant 20? What do I do? Well, I just assign factorial of 20. But where is the factorial sub coming from? Oh, it's a line of code above. So what do we have to do? We're a compiler chugging through this code, and we hit this constant declaration, and we hit this statement. And we kind of like, I actually have to do something and run some code now. And it's not just that I have to run a bit of code here, this bit of code calls this subroutine. So it has to go off and say, oh, we were sort of in the middle of compiling this program, but we need a little bit of it earlier. So we have to go off and compile that subroutine there, okay, just in time, so that we can actually call it. And of course, you can combine the two. Okay, so the compiler has to be re-entrant. So here we have a begin that doesn't eval. And yeah, you can have a begin that doesn't eval, that doesn't begin, that doesn't eval. You can go as deep as you want. Well, that's just not having local state. That one isn't quite so bad as the previous one. This one's fun. The grammar is mutable. Okay, so what if I wanted a factorial operator? Well, I can declare a subroutine. Okay, as a postfix. As a postfix operator, we put the name of it in there. We take the operand. We make a range from 1 up to an operand. And this is called the reduction measure operator. So you take an infix operator like multiply, you surround it by the square brackets, and it basically takes the numbers between 1 and n, and multiplies them all together, which is factorial. Very nice. But these things should only apply lexically. We don't want it, so if somebody is writing a module, and they go and declare themselves a new operator, and they then import the module and they just had it for that internal use, we don't want their operators to start leaking all over the place. Okay, that's one of the general design principles of Perl 6. Sure, we'll let you tweak the language, but you're going to have to write a use statement or declare something to say you're going to do it. We always know what language we're meant to be passing. So at the end of the scope, subroutines are all lexical in Perl 6. That's the default. So at the end of this scope here, this has to become a syntax library. Okay? So it's not just that we have to be able to augment the parser, it's that we actually have to be able to sort of switch in to passing Perl 6 plus an extra operator in this block. And then when we fall out of it, we need to go back and say, oh, that was the language we were in before. And of course, these can nest as much as you want. So you can sort of create all of these various nested languages. And it's not only that, it's that the way that we pass is actually building up these sort of just-in-time state machines to do the passing. So we actually have to factor the new operators into those as well, otherwise we might get the wrong pass. Then there's metaprogramming. So we have keywords like class, module, grammar. and you sort of look at them as a sort of Perl 6 new programmer, and you sort of say, oh yeah, well, they're built-in things. Yeah, well, they are. But that doesn't mean you can't change what they mean. So a while back, I wrote a module called Grammar Tracer. And what it does is it basically takes a grammar, something that we use to parse. And so there's the JSON tiny, for example. What it does is it traces and draws you a nice tree showing you how your grammar parses things and where it goes wrong. How is it implemented? Well, it's implemented by changing what grammar means. So we actually, when we hit these keywords, their meaning might actually be changeable as well. So we can't just hard code one meaning or one implementation of class. So that actually leads us on to another problem, because we sort of realize that, okay, as we go and parse a class, we create an object that describes the class, and then we go and create a method which creates an object that describes the method. So we have the whole sort of meta objects things here. But what next? Because what happens if we need to, if we just need to go and run the program straight after we compile? Well, that's okay, the objects are sat in memory. But what if I want to, take the built-ins library, which is 13,000 lines of code, and compile it down to bytecode and then just load it? Well, then I need to be able to serialize all of these objects. So we actually have to go serializing. And that's kind of fun, because, you can actually do things like this. You can write a begin block. You can create a new type, call it foo, very creative, and then you can actually shove it in the export namespace. And now we've actually just created this arbitrary type without even actually writing a declaration, a proper class declaration. So we have to handle this, and of course, you can screw around with stuff. Augment is the way you take an existing class. This is the int class, which is in the core setting, and we add an extra method to it. And if you do that, well, what do we do now? Because we've gone and changed this object, we've already serialized it somewhere else. Well, we have to detect the change and then re-serialize a new version of the thing. So there's all kinds of sort of fun going on inside of here. Then there's optimization problems. Okay, what's an operator? Well, it's a call. Okay, when you write a plus b, it calls infix plus on a and b. And then we have, this is a multiple dispatch. It's a call that has a bunch of candidates. So we have one for integer addition, we have one for floating point, we have one for rational. And you can imagine that if we actually do that call for every single time we write plus, well, yeah, that's really going to be nice and slow. So we actually need to do what we call inlining. And to do that, we have to be able to analyze calls like this at compile time. And if we're going to analyze calls like this at compile time, we need to build a very rich model of the program in order to be able to do that. And it's not just the types, like int, are things we can look at and always know what are. People can not only introduce their own types, which is fine, but because we support metaprogramming, they can change what type checking means, which we also have to take into account when we sat in the optimizer making decisions. So basically the way that we kind of started out in Rakudo is that suddenly a lot of the thinking was very conventional. We built a relatively conventional compiler. The grammar engine was pretty innovative. Patrick Lee showed a really nice job there. We ended up doing the parsing very well. But there was a lot of things which, because we'd adopted a sort of relatively everyday compiler architecture, what we kind of found was that certain things were not handled or were not handleable very easily. Every time we had to do something at begin time, it was horrible. Every time that we compiled the class, we hadn't got to the point of having figured out the serialization thing. So what we'd actually do is we'd compile your class into a set of instructions which basically ran at startup and created all the measure objects, which is kind of okay, but not very fast. So we made a lot of things work. On the outside it looked promising, but in the inside it kind of felt like mowing a hedge like that. And I mean, it works, you can do it, but if you have to mow your hedge like this every day, You know, I mean, the end user doesn't necessarily notice the problem. They just see a hash that got mode. But you know, if you're the guy doing this, you're sort of looking at this thinking, no, we should not be doing this. And this is kind of what it started to feel like as we started to sort of build more and more features into things. And I kind of think this happens in a lot of projects. It's sort of the ignorance curve. You know, you start a project out, any project, at the point of maximum ignorance. And hopefully at some point you sort of have an aha. This is the point where we sort of finally sort of grasp what we're trying to do. And actually for Rakudo, if you followed the development, you'll know that there was a branch that was called non. It stood for new object model, and actually ended up doing a lot more than that. And basically this was the point where, you know, it was kind of the aha, we really must actually build different. You know, so one of the problems that we realized was that the grammar and actions needed to be split up differently. We needed a third thing that took care of declarations, and that could have been scattered all over the place before. We needed to make this whole object creation during parsing and compiling just a really easy thing to do. In fact, we needed to make the whole begin time handling just an easy thing, so that it wasn't an ordeal in all of the different places that we needed to do it. So basically this set of things which do not, you know, really handled in a clean way in the original architecture, you know, we came back and said, well, these, you know, we can't afford to treat these as these sort of weird special cases. They're not very special. They're things that happen all the time. Now, around the same time this was happening, we were sort of aware that languages like Ruby and Python were getting ported to other virtual machines. So we had Iron Python and Iron Ruby on the CLR. We had various forms of those languages over on the JVM. And so the one question was, well, why not Perl? Why should we not have Perl 6 there as well? And, you know, Perl 5 runs on loads of platforms. It's great. The thing is that the world has sort of moved around it, and these days a lot of the interesting platforms are not hardware and CPU combinations, they're virtual. So you can find places where their policy is we deploy anything that runs on a JVM. It doesn't matter what language, it doesn't have to be Java, it just has to run on the JVM because that's what we run. So if you want to run everywhere, then a bunch of the everywheres these days are not about, you know, physical hardware things, they're about virtual environments. If you want to be able to run everywhere language, you know, provide ways to do it on all the platforms. These virtual platforms kind of matter. So we're kind of aware that, you know, we really needed to do this as well. And one of the sort of things we realized is that building all that we've built so far has been very arduous. There's a lot of work. So we didn't want to sort of build this in a way where, just like with, you know, the languages like Ruby and Python, what we would do is we would go off and just implement this, you know, as Rakudo and Parrot, and we'll just leave the other ones to someone else. We kind of realized that it would be really nice if we could reuse the investment that we've done in getting this stuff done, and then just plug it into different ways of turning that into code for, say, Parrot, for JVM, maybe for JavaScript, and these various other languages. So the grand plan was basically, you know, do this extensive rework to solve those underlying architectural problems. Get rid of all of this mess and the things that were really hard to do, make them relatively easy to do because we have the right primitives. We didn't go all the way into all the things, we just tried to get the architecture in shape so that it would be possible to get all of these things righter as we went along. That actually ended up taking longer than we imagined. Many people whined. This is one of the great things if you sort of make the hard decision of we really should do the right thing here. You know, people look on the outside and say, oh, you had all of these things working already. And you kind of had to be on the inside to sort of know that, yeah, well, that was all very nice, but we were, you know, the cost of getting each next thing was just going up and up and up. So, you know, it kind of had to happen. Now, one of the other questions is, what are we writing all this stuff in? And that actually became very important as soon as we knew that we would want to port this to other backends. So initially, we wrote pieces of it in a language called NQP. NQP is not quite Perl 6. It's a small subset of Perl 6 that we use to build the compiler stuff in. And early work had sort of used this, but we've then written loads and loads of stuff in Parrot's assembly language. Now, have you ever tried to maintain anything really complicated in something that's essentially an assembly language? You kind of do it once in your life, and then you realize that you shouldn't. Yeah, well, anyway. But the other problem was that it sort of meant that for people to contribute, they had to go and learn this. And it was sort of making it harder for us to grow the contributor base as well. So essentially, we ended up sort of saying, well, we'll just write all of this in NQP. We'll, apart from a bunch of the built-ins, which we'll write in Perl 6 itself. Even NQP ended up being written in NQP. So it became a self-hosting compiler. And this would prove really important for the porting method. So the overall architecture we arrived at is Rakudo, which has various pieces in it. I don't need to talk too much about them now. And then we have NQP, which is bootstrapped and written in itself. And these basically sort of boil down to some kind of VM abstraction layer. And then we have various VM specific bits. So this is kind of what we ended up with. And after sort of we've got all of this done, we've got a bunch of sort of nice features in place and so on, and it was time to start working on the JVM stuff. The plan was that all of that stuff at the top and some of that stuff down below would stay exactly the same, and we just drop a couple of new pieces in here. So was the plan. So the first thing was that if we're going to write this in NQP, we need a way to make JVM bytecode from NQP code. So I came up with something called JAST, JVM Abstract Syntax Tree. Basically, it's a small tree representation of JVM bytecode. So here you can see we have a method. Its return type is I, the integer. It's going to put a constant 1 on the stack and do a I return instruction. And essentially, I then just built this up with a bunch of tests. So at this point, I had a way to get from something I could build in NQP to a piece of JVM bytecode. Now, I didn't actually want to do the bytecode implementation. Generating all of these byte streams, that would just be really boring. So I basically dumped out a bunch of text from the AST and then fed it to a program that was written in Java that turned that text into bytecode. Now, at some point, now we have it all in process, we'll throw away the textual stage, and we'll go straight from the tree to the bytecode. The second step was to turn that higher level tree, that thing that we get out of the Perl 6 front end, or the NQP front end, into something low level that we can run on the JVM. So basically that involved doing a lot of the sort of porting of runtime support. I won't go into all the details there. But essentially this was the second step. And again, I built a bunch of tests. So here's a chunk of cast, it's a block, it does a say, okay, and here's the thing that we're going to say. And the thing about this is it's much higher level than the JVM bytecode. We're not sort of doing all of the stack operations and so on there. So what's happening between here and the JVM is we're basically turning this into the other tree, and that tree is then getting turned into JVM bytecode.
Question.
Yep.
Is it fair to say that this JAST thing corresponds to Parrot's host?
Yes. Yeah, basically.
But is that a script?
Not really. They're playing the same role. It's just that, the JVM is a stack machine. Which means things end up factored a bit differently. That's not as important as it might seem at high level. The two, generating register code and generating stack code are different, but it's not like one is harder than the other. They're just different hardware. So, yeah. Okay, so next.
Hey.
Huh?
Can you go one step back?
Can I go one step back?
Yeah. This one, right. So you said that AST is from abstract syntax tree because abstract of the virtual machine. So now it's JVM abstract syntax tree, so how is it abstract?
No, this is abstract from the virtual machine. This is the thing that the Perl 6 front end produces.
Okay.
So what my test is doing is it's saying if I take this AST and then I feed it to the JVM translator, does it do the right thing? So does it actually say that string to standard output if I run the program that it produces?
Yeah, when you said it corresponds to post, and post was about opcodes index.
Post is the parrot thing.
Yes, I know, and this is JVM thing, but...
No, just corresponds to post.
Yes, I'm
cast.
talking about just, not cast.
Okay, just is that one though. That's, that one's
Yeah,
just.
this one.
That
So
one.
is it abstract as well?
The AST is a bit of a stretch there. I'm not quite sure why it ended up being called an AST in a way.
Alright.
Just because JASP was something I could say in one word.
Jost.
We could have called it JOST, which is Java opcode syntax tree. Yeah, we could have called it that. I mean, it's sort of, the assembler does a bit of work to get it all to work out, but it's fairly thin mapping. Well, you can submit a patch and call it JOST if you want.
Okay, I'm doing that right now.
Oh man. You'll have fun writing that patch because you'll also have to take care of the bootstrap.
Oh my, okay.
Yeah. Okay, so basically at this point was the sort of big moment, okay? Because this was where we would test if one of the big theories of the whole project worked. Basically, can we take the existing NQP parser and grammar and actions and all of that stuff that we built to originally target Parrot, and then instead of it going and generating code for Parrot, we just go and plug in, after we get the cast tree, this new JVM backend that we've been building up with all of these tests. And the answer was yes in about 20 lines of code. That's... So this is sort of one of those times where I look and say, yeah, our architecture has some good properties. The one I did last year was when I managed to write a debugger without changing a single line of code in Rakudo, which proved that another part of our architecture was sufficiently abstracted. Nice. So yeah, architecture win. Design pays off, and this was designed on the multi-year scale. The stuff that I did to try and work up to this has basically ended up being a couple of years worth of work. Even if the stuff that's happened to do the JVM things has been less than 6 months of work. So. Okay, now one of the really nice things, if you do this right, is that now we have something that we call a cross-compiler. It's running on Parrot, but it's running the JVM sort of back-end production stuff, so you have a cross-compiler. You have an NQP that's running on Parrot that churns out bytecode for JVM. What can you do with that? Well, since NQP is written in NQP, then what you can do is you can take NQP's source code, throw it into your cross-compiler, and out at the other end pops an autonomous, not dependent on Parrot version of NQP that runs on the JVM. So basically you don't actually port the thing. Alright? You get NQP to sort of spit itself out on a new virtual machine. Which is really nice. That's sort of one of the, that was the second big payoff. So basically the job really was write the new backend and then just get NQP itself to cross-compile itself, and then we had NQP on the JVM. Nice. So there we had it. At this point we had a self-hosting NQP. Now of course that just leaves us one more question about NQP. Which is a slightly mind-twisting question of, can NQP running on the JVM produce a new version of itself that runs on the JVM from source code? Don't think about it too hard. But basically, the answer was yeah, yes, eventually. There was a few sort of things I had to do. So eventually, we ended up with an NQP on JVM that could build itself. So now, when you go and build NQP for the JVM, you just need a JVM. You don't need any Parrot dependency or anything like that. And if you want to build NQP on Parrot, you just need Parrot. You don't need a JVM dependency. So you just need the back end you're going to build the thing for. We ship the stage 0 compiler for each of them, and it just builds the latest source. Question?
So no more need for Parrot at all anymore?
Sorry?
No more need for Parrot anymore?
If you want to run NQP on the JVM, then you don't need it. If you want to run NQP on Parrot, then yeah, of course you need it. So, yeah, so you have a choice. And you don't, the point is that you only need the platform that you're going to build it on. So we're not cross-compiling it. We actually, we actually can do the whole thing on JVM if that's what you want to build. Yeah. Okay, so what about Rakudo? Well, yeah, that's some fun as well. The thing about Rakudo is most of it turns in an NQP. And we could now actually have an NQP compiler that ran on the JVM. Okay? So in theory, all we'd have to do is get the NQP on JVM compiler to compile the Perl 6 compiler. And then we'd sort of be a long way there. Well, kind of. So this bit went pretty easy. This bit over here is the thing that parses Perl 6 and figures out what Perl 6 code means. So that bit wasn't too bad. Then we have a bunch of stuff called meta objects. Meta objects are the things that say, well, what does class mean in Perl 6? What does role mean in Perl 6? What does grammar mean? So essentially it implements the type system. So we had that bunch of code in NQP. Then we had this thing called the bootstrap. Now, while the Perl 6 grammar and actions were basically not a big problem to get ported. I mean, NQP is a subset of Perl 6. We could already do that. It's nothing new. It's just bigger. So that wasn't a problem. The meta objects are kind of the same. NQP has a bunch of its meta objects. So this is just the same, but bigger. The bootstrap was a bit of a different story. So the way that the Perl 6 bootstrap works is instead of piecing its type system together every time you run it, because we have serialization, what it does is it has a huge begin block. And I mean huge. It's like 1,000-line long begin block. And what happens is it runs that begin block, which produces all of the objects, and then we serialize them. So we don't have to do the work every time you start up Rakudo. This is the point back in Rakudo's history when we introduced this, when our startup time basically went from, a second to 0.2 or 0.3, depending on your hardware. Quite a big way. So, once you have all those, okay, so at this point we have this piece, and then we get to the core setting. This is where all of the built-ins are. Okay? Now the core setting is written in Perl 6, which means that you need a Perl 6 compiler to build the sort of rest of Perl 6. And it's about that long. Okay? There's 13,250 lines of code. And this is the first test that I have to do on the compiler running on the JVM. So should I sort of, try and cut it down somehow? Should I try and do a setting light? And I sort of thought about this, and then I was like, screw it, let's do it all anyway. So basically, it works like this. Getting from line 0 to line 100 took about a week. And then people were teasing me like, oh, 100 lines a week, this will take a while. So then I got from about 100 to 1,000 in a week. So then it started teasing me about, oh, it's 100 lines a day. Then I started going from like 1,000 to 2,000 in a day, and then 2,000 to the whole 13,000 actually with just one more day. So it all went like that. What you're hitting at the start is every single possible problem. Now, the problem with doing this stuff is that you're not actually just trying to get the thing to pass. If that was all we had to do, then it wouldn't be so bad. The thing that makes it a little icky is that at line 137, you hit this. It's a begin block. What does a begin block mean? It means you have to run it. What language do we have to run? We have to run Perl 6. So you can't actually build the Perl 6 built-in without being able to run Perl 6 code. So basically, I couldn't actually compile the standard library without being able to run pieces on it. So that was fun, and that meant that by the time I actually got the pass to finish, it actually implemented most of the runtime support to actually support running Perl 6 code on the JVM. So finally, around a week or two ago, Perl 6 -E. This is running on the JVM. Okay, say hello JVM, and it popped out hello JVM. That was much happiness. So, we can do hello world. Can we do anything else? Yeah, actually, a reasonable number of things. So, one of the things about working your way through the core setting is it actually touches quite a lot of pieces of the Perl 6 code, including even doing some very basic listy stuff, definitely doing a load of hashes. There's a whole load that actually does work, and then there's a whole load that kind of doesn't. So the thing about this though is that basically we've got the entire standard library cross-compiled. So it isn't a problem of can we compile it anymore, it's just a problem of which bits don't actually work. So what's coming next? The next step is pass the sanity tests. basically a bunch of basic tests that test can we do enough to actually run the test harness, the test module, test PM. So these are just tests that spit out tap using a bunch of say instructions. Okay, so they don't really use a proper tap module, they use say, like that. And once we can pass those, then we are able to compile the test PM, which means that we can then start attempting the specification tests, of which is about 740. So, sorry? 756. Okay. Did you just take the number of lines in spec-test.data?
No.
Okay, good. Because if you did, you have to remove the comments at the start. Okay, well, fine. My job's done. More time. So basically, the goal is to get through that, and then after that, it's going to be a case of getting the ecosystem up and running with this. So it's going to be teaching things like Panda, which is the module installer, to be able to install modules when we're running at the JVM as well. I wonder if Tajik is around somewhere. You're here. Hello. Hey. I will be talking to you soon about Panda and JVM.
Right, cool.
Awesome. So, Tajik made Panda. It's great.
It is?
It's because it's really good if we get to have pictures of cute pandas everywhere. Performance. Okay, big disclaimer time. I haven't optimized this yet. Okay, so the numbers that I'm going to show you are the numbers that we get before I actually spend time getting it to go fast. So basically, this is a case of sort of make it work at all, and I'm still very much in the make it work at all phase with the Perl 6 stuff. We can do hello world, we can sort of do some of the basic sanity tests. So the numbers you're about to see are not sort of the end game. This is the baseline from where I'll start. So here they are. If you run one of my guys, Nick Clark, has been running very regularly a Levenstein benchmark, running in NQP, not in Perl 6 code, but in NQP. He's reporting that on the JVM backend, that runs about 15 times faster, which is a good start. One of the things that sucks about working on Rakudo is that you spend quite a lot of time waiting for the core setting to compile if you change something in it. So you change it, you sit around waiting for it to compile. The pass phase of that goes about 3 times faster on the JVM, which basically means that not only does that mean that program pass a bit faster, it means that we're going to be able to build Rakudo faster, which means it's going to reduce our development cycles, which is going to be kind of nice. And if you just do a stupid while loop benchmark, this is something that Rakudo is capable of running on the JVM now. That comes out about 5 times faster. I think we've got quite a lot of potential improvements to do on that, all of those. So basically the baseline before I start optimizing is anywhere between 3 and 15 times faster in what we've observed so far. That's not a bad starting point before I actually focus on making it faster. So, yeah. So, we definitely have work to do here, but it's a promising start. When? The June compiler release of Rakudo will be the first one to ship with some level of JVM support. I'm not going to commit to how much that will be, but it will be at least hello world. I have between now and when the next release happens in June, which will be around sort of the 20th-ish, I guess. We have plenty of time to get further. My aim is that around the August release, we should be doing pretty much all the spec tests. I think we can get there. Beyond that, I hope that we'll also be working towards the ecosystem. So my aim is that Rakudo Star, which is our distribution release, so the compiler releases are just a compiler. The Star releases include also a bunch of modules, the debugger, and all of those things. And I'm aiming for something like September for that. One of the nice things about the debugger is that it's written in NQP on Perl 6, which means that it should just work on JVM without any extra work, which is kind of nice. So the good things about using the JVM to run Perl 6, it's mature, it's well optimized, it's been around for ages. They do some scary optimizations. They inline like 9 levels deep by default. That's pretty crazy. The other thing that makes the JVM especially interesting is that they actually have been doing quite a lot to support languages, not Java. That includes this new instruction called invoke dynamic. You might wonder what one instruction is as a contribution. In fact, invoke dynamic may be one instruction, but it's actually the gateway to a huge framework of things, which basically, if I had to summarize it in a sentence, it's like you can teach to JVM how your language works. And it's not just teach to JVM, you're teaching the JVM's JIT compiler how your language works. So instead of us having all of this bunch of dispatch logic for methods, which of course we have to have because Perl-6 method dispatch is kind of interesting, we can have it, but we can keep it off to the side. And we can actually tell the JVM, look, this is what it means to call a Perl-6 method, and here is what we resolved it to, and here is a guard clause so you can look at it in the future and know that if the type matches, just go there. And for subroutines, we have it even easier, and what this means is that we can actually teach the JVM enough about Perl-6 without changing Perl-6 semantics. We can teach it enough that it should then be able to start doing a bunch of its optimizations for us. So the inlining that the JVM can do should start applying to the Perl-6 code. So that's a very powerful potential. One of the other things is they built this very much thinking about dynamic languages. Perl-6 is, as I mentioned, gradually typed. It's, you know, you can do static stuff and you can do dynamic. So the JVM is kind of interesting in that sense as well. That, you know, it's at the end it's a lot for static language, Java, and now they're trying to make it do really well for dynamic, so we can draw both of them. It also has very solid and battle-hardened threads. It's, you know, they're very well used, very well exercised in the real world. So my expectation is this is where we can really start making some hard progress on, you know, nailing down the threading model in Perl-6 and getting that practically usable, which is going to be very exciting to do. I'm looking forward to that. Weaknesses, startup time is currently awful. Like really awful. So, yeah, part of it is actually just the JVM takes a while to start up. Part of it's this perfect storm. The JVM is slowest when it starts, and then as it learns about the program, it starts optimizing things. What this means is that everything that we do at startup is especially expensive. So we're going to have to do quite a lot of work to cut down on that. I think a lot can be done. It's on my to-do list, but getting stuff working was sort of priority one. So I think that if you look at it and you're like, gee, the startup time really sucks, yeah, it does, but I think we can do better. Invoke dynamic is something that they seem to be taking very seriously. They're going to use it for the lambdas they're putting into Java 8. Can you believe that Java can do like functional programming after all these years? Wow, Perl was only doing it in 95 or before, or probably ages ago. But anyway, it appears they're fairly serious about invoke dynamic, but it only went into the latest JVM. I actually managed to find bugs. I managed to segfault the JVM. Feels like an achievement. So there's plenty of work to do yet, of course, but that's just working. We've come from nothing to this far, so that bit doesn't worry me so much. In general, I think that, you know, with Perl, we always have this more than one way to do it. With this JVM work, we've sort of shown that it's possible to build a Perl-6 implementation that can be run on multiple different backends. I think it's kind of telling that the naive, first, unoptimized cut of getting this to work actually has performance characteristics to exceed the initial implementation on Parrot. So I don't think that we've got into the dilemma where, you know, we have it implemented on one VM and every other port has to be slow because we made a load of assumptions about how a VM looks. We seem to have hopefully escaped that trap, at least the initial numbers suggest so. So, you know, there's more than one way to do it. There's more than one way to run it. Will we have a back-end explosion? Well, we only have so many resources. For me personally, I expect to put my resources aligned with popularity. So we'll sort of see which backends are getting used the most, and I'll try and focus my efforts there. Of course, I need to focus on a lot of things as well. But I'm not going to discourage anyone who wants to come along and work on any particular targeting. So if someone wanted to take what I've done and say, let's just get it all shoved over to the CLR and try and run it on .NET, well, be my guest. I don't plan to work on that particularly soon myself, but I'm perfectly happy for somebody else to do that. So overall, my sort of vision for this is we end up with Rakudo Perl 6 that runs on a bunch of platforms, that's fast and reliable, and I don't have to worry about telling people use this for your stuff. That we have modules that you can rely on being available in multiple places. Debugger reliably works across these different places. And actually, the majority of development work goes into stuff that's shared. So we try and just get the architecture, much like we have so far, kept so that when you do most things, you're doing them so they benefit all of the places we run. And there's only a sort of handful of things which are very specific to any particular backend. So I hope that we'll very much be able to keep the majority of the effort relevant to all of the things. And the fact that we've written so much of Perl 6 in Perl 6 or in NQP is sort of a key part of doing that. And at the end of the day, I hope we'll have people using Perl 6, building awesome stuff, having a lot of fun doing so. Okay, I think that life's too short not to enjoy ourselves. So I want to make this an enjoyable development experience. Okay, I'm not sure what I did when I took my time budget, probably something terrible. But thanks very much. I'm not sure if I have time for questions.
The Perl 6 is just a batch file which calls Java binary or what?
Yeah, it is a batch file. Or on.
I'm curious what is inside. I expect class and something.
We generate an SH on. It's a very long line. It's a really, really long line. Yeah. But you don't want to type this by hand, which is why there's a batch file. But yeah, it generates an SH over on Unixy places. So yeah, that's part of the consistency thing. It's kind of nice if you build it and immediately you just know how to run it the same way you already knew how to run it on any other backend. So yeah, that's how it works.
Can we run it, or it just works in your?
Sorry?
Can we run it, the code, or it just works in your laptop at the moment?
You can get hold of it. At the moment, you have to grab a particular branch of NQP and build that, and then a particular branch of Rakudo and build that, and then you can get it. Other people have got it to build, so you can do it. What's going to happen sometime in the course of maybe the next week, probably the next week, is I'm going to merge those branches. So well in time for the next Rakudo release, it'll be in the main line, and we'll then just have it as the normal thing. It's just that instead of running Perl configure PL, we'll run Perl configure JVM.pl and then make. So
this Perl 6 generates class files.
We generate a class file per compilation unit. So if I go and I look in here. No,
Or
not
different
there.
way. PM files, they are generated to class files or?
Yeah, so if you look through this, then we have the PVC is the parent version. We have an actions PM or an actions NQP, because it's written in NQP, but we just get the file extension like that. But it was a Perl module, it would be actions PM. And you can sort of see that we've got an action.class. So basically your PM file becomes a .class file. It's also interesting to note the precise comparisons, by the way. Sometimes we come out ahead. And the code that the JVM produces is smaller, and sometimes it actually comes out bigger. And there's some interesting work to do to nail that down. But yeah, it's a class file.
Back to one question.
Okay.
One question. You mentioned that Perl 6 is currently running on multiple platforms. Am I right that those platforms currently are only Parrot VM and JVM? And the
Yes.
two platforms count as multiple?
Well, what I think I meant when I was saying that is that when I say we already run on multiple platforms, I was meaning the hardware, CPU, and so forth sense.
Yes, and while we are at that, you have probably heard about the PyPy. It's 3 years younger than Perl 6 effort, but the guys do amazing work, and Alex Gaynor currently works on Topos and has some amazing results. Was there ever a suggestion to write a Perl 6 implementation in R Python?
There's certainly been a suggestion that now we have the ability to write backends, and we've proven that we can do a JVM one that, yes, a PyPy one would be interesting to do.
Because PyPy, you see, it currently works and is deployed in much places as in production.
Yeah, sure. That should be possible. I don't see anything that would make that not the thing that we can do. So, yeah, that could well happen. I think that getting from 1 to 2 is sort of the really painful one, because you find all the places that are not really abstracted properly. Now that we've got from 1 to 2, I suspect 2 to 3 will be a much easier job. So, yeah, I can definitely see something like that happening.
Thank you.
Any more?
How do you see the landscape of backends changing in the next few months, now that we have the JVM?
Well, I think that the interesting thing that we'll need to look at is, what do these backends serve, or who do they serve? The JVM will serve a couple of niches very well. One will be people who actually want to run stuff on the JVM explicitly. Another bunch will be people who don't really care how long their thing takes to start, but they do care that it runs a bit faster as it goes. I think the very mature threading support of the JVM will also be very relevant for that sort of side of things as well. For people who want to sort of run Perl 6 in a way where they care a lot about fast startup, they care a lot about sort of having something that doesn't come with all the baggage that a JVM does, that is much smaller and much more focused. I think that you have to sort of say, well, the JVM probably can't serve those people, and that's probably where the focus will be. So for me, the focus is not on saying let's do the CLR now, because fine, we can do it at some point. There's already the edge there. For 2, I don't think it serves a particularly different or particularly sort of large niche that we won't cover with the JVM one. So, my focus is going to be very much on backends that sort of add something we don't have. So, yeah.
Excuse me? I'm very sorry for jumping in again, but the point of running on JVM is often to make use of existing Java libraries.
Yeah.
Do you have something for that?
Not yet, but we'll have. Basically, the way Perl 6's object systems work is, it's all meta programming.
It would be killer.
So we can, the way that I want this to look is basically, we type in the text editor here. It'd be kind of nice if we can use, Java, util, whatever, from, JVM, okay, and then something like that. That's what I'm going to aim for. And there's no technical reason we can't do that. What's going to get really interesting is if we can take the call sites involved with these and then hide all of the marshalling stuff behind the invoke dynamic.
So that's in Perl 6.
The call and from, I believe. Yeah, this would be very cool. Again, it's on the to-do list. I just want to get Rakudo running useful stuff first, and then this will come a little bit after. Or somebody will task steal it for me. I always like it when people steal interesting tasks from me, because then they happen sooner. Okay?